kind of message. Now it is started. Okay. Okay. Confirm whether you can see this slide.
Yes, sir.
Yes, sir.
Okay. And I'm trying to write welcome at the top, whether you can see it. Is it visible to you, this
Yes.
welcome
Yes,
order?
sir.
Okay, good. Yeah, so let me start. So today we'll just introduce the topic, and basically I'll tell you what is this subject about and a formal definition. Then what are the main content of a power electronic converter? What are the different power electronic converter? I'll also talk about their applications, right? And you'll be amazed to see there are so many applications for this topic, and it is really a good area to work on. It is not saturated, still a lot of research is going on. And I'll also tell you what we are doing in this area, some of my team's work, and if you're interested, then either you can also contribute to us, right? Because as a team only we can progress. And course structure, timeline planning, everything is there in that syllabus document. If you want, I'll spend some time. Otherwise, everything is clear there. And on the syllabus document, you will see I have used, we have already given you reference books. So try to get them, right? Hard copy, soft copy, whatever, in a legal way, right? You can buy them from soft copy, etc. Yes, okay, yes. I know how you will handle it. So let me discuss this here. So get them, and if you are not getting any particular resources, let me know. I'll try to help as much as possible. Okay, right. So let me introduce you more to this power electronics. What exactly we do? Okay. So power electronics deals with power processing. Okay, or we sometimes we see this energy transfer, and between what it does from electrical to electrical only. That is the requirement. Okay. For example, you might have studied electric motor. It have electricity at the input, mechanical power at the output. Okay, a generator will be reverse, right? Mechanical input, electrical output. But here in this power electronic system, your input is also electrical, output is also electrical, right? So we basically deal with converting something from one electrical to another electrical side. And while doing it, we stress on three important C's. Okay. One is efficient conversion. I'll be doing some sort of conversion. Okay. For example, DC to AC conversion. So that is the meaning of conversion. The example is DC to AC or AC to DC. That is conversion. Then control. Okay. So by the term control, we are meaning that, let's say I want to convert DC to AC. Then at the output, I want something AC, and I want to control that voltage, frequency, phase. Okay, maybe I would like to control my AC amplitude at 230 volt. Sometime I want it to be 100 volt. So even though there will be some load changes, input changes, right? My output should remain at as per my desired value. So that is roughly you are referring as control. Another is conditioning. Okay. So in power electronics, you will see that we are using switching. Okay, several times we'll be turning off a switch, turning on of a switch, and as a result, uh, the output won't look exactly what we are looking for. For example, if I want a DC output, I want this kind of output, flat DC, right? But in practice, what after power electronic converter, we might be getting something like this, whose average value is same as that what we want. Okay, but actually output will be something like this. So then what we do, we use some sort of filter. so that I can eliminate those high frequency pulsation and I can finally achieve with a DC or a sinusoidal AC output. So that is the meaning of conditioning. I'll tell you more about this. I'll be giving you some example and how to design filter. Everything we'll discuss. So this is more or less the important 3 C's in this power electronic converter. So we want efficient conversion. We would like to control the output. Sometimes we would like to control the input also. Okay. For example, solar photovoltaic system. We want to control the input voltage or input current. Then conditioning of electrical power flow. And all this we want to achieve by using static component, right? So if you take an ulta example, a reverse scenario, in electric motor, we convert from electrical to mechanical, but using rotational means, right? But here, there is no rotating part involved. Everything is going to be static, fine? And in this conversion, we'll be converting from electrical to an electrical, that should be clear to you. From now, we'll convert from one form or level. By form, I'm meaning whether it is DC or AC. By level, we are roughly referring to what voltage level typically or what power level, okay, to another form or level. So this will take up some example and you will see slowly. Okay. And basically, you'll be dealing with DC and AC systems. And if you just do this sequencing, how many type of converter we can have in power electronics, you will see that I can convert from DC to DC, right? And then DC to AC, AC to AC, AC to DC. So basically, there are 4 types. Now you may ask, sir, it is already DC. Why you want another DC, right? So those things we'll discuss with example. A lot of my non-electrical friend ask this question that Baba तुमको DC to DC converter क्यों चाहिए? इधर भी DC है, उधर भी DC है. Why do you want that? So I'll give you an example and it will be clear to you later on. So remember, we need 4 types. Okay, DC to DC, DC to AC, AC to AC, and AC to DC. We'll take up some example also in next slide. Right. So now, if I ask you that, let us think about a solution. So let me tell you, this power electronic solution become popular in late 90s. Okay, basically around 1950s, we had this power semiconductor switches. You might have heard about thyristor, IGBT, MOSFET, right? Diode, example of semiconductor switching devices. So before these devices came into existence, how people used to convert, let us try to understand. And after you getting these semiconductor switching devices, how we are converting, that let us try to understand. So if I ask you that, let's say I have a 100-volt DC somewhere, okay, maybe a battery, and I want a 30-volt DC or a say 50-volt RMS AC. Okay, how do you convert? So before power electronic system, one of the solution to handle this was first convert this electrical energy. Here you see both of them are electrical, right? So first you convert electrical energy to a mechanical energy. Okay, how? Simply use a motor. Then that mechanical energy you convert back into electrical using a generator, right? Now by controlling generator excitation, motor speed, you can actually control your output, what you want. If you are using a AC generator, you will get AC, DC generator, you will get DC output, right? So that's how people used to control long back when before power electronics. So you know this system used to be very bulky, then noisy, rotating parts were involved, so a lot of maintenance issues. So those were the problem. But after power electronic came, we could convert electrical directly to electrical, fine. And you will see that in this conversion process, we are using only mainly 3 type of element. One is this switches, different type of switches, then inductors, sometimes transformers, and then capacitor. Okay, these are the main component in a power electronic converter. We don't want additional resistance inside the converter. Resistance can be a load to your system, but not the main power conversion process. So you can see ideally all these elements are lossless. Okay, so this conversion process, which is based on these three basic elements, so that will be efficient. And just turning off a semiconductor switch on and off, it doesn't need to produce noise, right? And there is no rotating part. So a lot of advantages are there, but we have also some disadvantage. Power quality, I told you, right? If you're doing some switching, you may not get a flat DC. It will be some pulse kind of. You may not get a proper sine wave. It will be some zigzag kind of sine wave maybe. Okay, so those will learn slowly. Then complexity of control will come, but nowadays with this superly powered microprocessor, digital signal processor, FPGA, all these things are there. So this control is also not a challenge nowadays. Fine. So we'll discuss slowly about more of this in later slides. Right. So quickly, I'll tell you the formal definition of power electronics, and you'll see ultimately it ends up with these basic terminologies, and just follow this definition. Okay. I mean, I'm not going to discuss this, just get it done. I hope you have understood little bit. Let me quickly check. Okay. Just give me the answer maybe in the chat box, or you can tell me in the mic also. Okay. So first question. Power electronic converter consists of rotating, not rotation, sorry, rotating as well as stationary parts. It is true or false? What do you think? Rotating as well as stationary. It is true or false? Answers? Achha, some of you please turn on your mic. I can't see the chat box. I have to log in. Huh? Give me the answer. It is true or false? False, right? Because we are not going to use any rotating system. That's pretty easy. Good. Okay. What are the three important C's that we discussed?
Conversion, control, and conditioning.
Okay. Is very clear. Okay. This one.
Electrical to electrical.
Electrical to electrical. Very good. Yeah. We are basically warming up, huh? This morning class and this is very easy questions. Okay. Question number 3. How many converter type you have in power electronics? By P, I always mean power electronics. Okay.
4.
4, right?
4.
What are they? What are they?
AC to DC, DC to AC, DC to DC, and AC to AC.
Good. Okay. Very good. Pretty easy, huh? Power electronics is actually very easy. Yes. Fine. Okay. Last question. Right. So, as compared to a prior art solution, what could be some key feature or advantages rather for power electronic system and solution? How a power electronic solution should be? What we want from it? Some key thing can you highlight?
There is no noise in the solutions. It requires less maintenance. It is lossless.
Efficient, right?
Yeah, it's efficient.
Efficient. Maintenance, less maintenance.
Yeah.
Maintenance. Okay. Another 2 key important feature that we want is it should be low in size volume. Okay. It should be very compact. We don't want a bigger solution, small one. So if I want to give you an example, do you remember how fan regulator used to look like long back? You used to rotate it by a knob, tech sound used to come and it used to get heated up, right? Do you remember? Have you seen ever that kind of regulator? Nowadays,
Yes,
you might be seeing a small regulator in your home, right? The circular regulator will smoothly rotate. So that is an example of power electronic converter. And earlier example used to be like this much, this length and this much white kind of box or brown box. Basically, it used to get heated up, right? Some of you, do you remember?
Yes, sir.
In older house, you might be still having this, but mostly now it is obsolete. So that is an example of non-power electronic solution. And the small regulator that you see in your home, behind that there is a small circuit, of course. It is not only that white knob. Behind that there is a small circuit where a AC to AC converter is involved. Okay, so you can understand what we are looking for. We want a very small, compact solution which should be efficient. How do you understand whether a system is efficient or not? If there is a lot of loss in the system, it will develop heat. Okay, you know Joule's law, right? I square RT. So whatever current is flowing into it, it's RMS square into resistance of that element into time. That turns up into heat. Okay, and you see those old regulators, they used to get heated up like anything. But you touch this fan regulator, it's very cool, right? It's not at all heated up. So that is an example of efficient and smaller compact solution. Okay, and all this we want to achieve using low cost. That is a bit contradictory. Okay, we want to achieve all this using it without paying much money. That is the biggest issue. We want high efficiency, low size, everything we want, but at the same time, when we don't want to pay more. So that is what are some of our expectations. Okay, good. So let me go to the next. Right. So we understood there are 4 types of power electronic converter, and in general, if I ask you that what are the main component inside a power electronic converter, okay? So eventually, power electronic system, as you understood, basically there will be a DC source or AC source somewhere at the input. The same thing maybe at the output. Maybe you want a AC source or DC output, okay? But in between, what is there? That is our power electronic solution. Okay. Achha, one more point. Whatever I am writing in this PPT, I'll be sharing you as a PDF maybe. Okay, with all this annotation in text. So you need not write too much thing. Just write what is absolutely mandatory. Apart from this, I'll be sharing you as a PDF with these annotations. So at the input, we have AC or DC. Okay. Output also we might be having AC or DC depending on requirement. So in between that, we have the power electronic converter. So we are trying to understand what is inside this power electronic solution. So of course, source and load is not part of this power electronic converter. That should be very clear to you. So what is there inside it? The main component inside power electronic solution will be semiconductor switches. Okay. In your home also you see some switches, right? When you want to turn on a bulb or fan, you use a switch. But that is not a semiconductor switch, right? That is just a mechanical switch. Huh? Then you might have heard about circuit breaker, relay, right? Those are also not semiconductor material, most of them, right? Conductor. Those are they mostly are based on electromagnetic principle. This relay, you know, right? That is not a power electronic devices or power semiconductor device radar. So semiconductor device example is you might have already studied diode, PN diode, right? Then BJT you must have studied, MOSFET, JFET, all those things you have studied. So those are the switches, and some new switches you will learn in this course: thyristor, GTO, triac. For example, in the fan regulator, I give an example. We use triac. Okay. And some advanced devices, if time permits, we'll also discuss. But these are the, you can say, heart of power electronic system, maybe. Okay, main component here. Then apart from these power electronic switches, so semiconductor switches, we also need storage element. Okay, to act as a filter. I told you, right? Conditioning. You have to relate conditioning. So control and conversion mainly is dependent on how you are handling these switches. Okay, we will teach how to do it, and we will do some simulation also. And conditioning mainly comes from the switching strategy, the way you are doing the PWM. Let me not tell PWM, we will discuss this later. And filtering is quite responsible for conditioning. And in filter, you know, we use capacitor and inductor. Okay, resistance we don't want to use in filter. Reason, we want more efficient system, no resistance, please. Okay, so let me write it in a bold font. No resistance is desired. Okay, only capacitor and inductor. Why? Because capacitor and inductor are lossless. Ideally, practically they also have little loss. We'll teach you how to calculate that and all. But we don't want any additional resistance. And sometimes we also use a transformer into the converter, inside the converter. So we'll see some circuit, then this thing should be much clear to you. So these are the main component, but to aid them, we need some other component also. Okay. For example, let's say if I want to control my output voltage, output current, I have to switch on and off in a particular fashion with particular time duration, etc. So how do you do it? Okay. One option is that you sit near the switch and you manually turn on and off. You see the look at the output voltage. If it is more, you off switch. If it is less, you on switch. Like that, you can do it. Okay. But that is not a good solution, right? If there are n number of converter, so already all of you have to be near those converter, and no one will attend the class. So that is not a good solution. So we must do a solution which should do this automatically. Okay. So all of you now, you understand concept like Arduino, Raspberry Pi, basic microcontrollers, right? So there I can write simple code and I can tell you, see, if I see output voltage is less, do this. Output voltage is high, do this. That kind of simple program you can write in your microcontroller, and you can drive these switches on off, point to on and to off, everything. So that is you need a microcontroller or a DSP, digital signal processor, or FPGA, those kind of thing. Okay, for programming, for writing the code. Then you need something like driver circuit, heatsink, etc. So those will learn slowly. Okay, sometimes you need to sense the output voltage, because otherwise, how do you know whether output voltage is less than required or higher than required? You need sensing arrangement. So this we'll discuss slowly. Okay, don't spend too much time on understanding each and everything now, because entire course will be there based on this different content here. Okay. So now I'll try to tell you. So I gave you a brief idea of how power electronic those elements look like. Now, if I ask you that how it looks like in lab, okay, let's say I ask you, please develop a DC to AC converter for me, okay, and I want my output voltage to be controlled, sinusoidal. So how do you do it? So typically in lab environment, we build something like this, right? So I'll tell you where is the switches. You can see these are the small switches. I don't know whether you can see it clearly or not. Maybe. So here these switches are there. Here also on those backside, it is not visible. Those switches are there. You can see 3 lines are going, right? So those 3 terminals are going to the switches. Okay. I'll show you some more image of switches, how they look like, and it will be clear to you. Next slide. And this aluminum thing, this is actually heatsink. Then this blue thing, okay, this is an example of current sensor. Okay. Then, of course, everything is mounted on a PCB that you can see. This is a sensing interface board. Okay. Then look at this thing you already know. It's a capacitor, right? These are example of driver circuit that I was referring to. And this is a DSP, or you can say you can even use a microcontroller. That is also okay. And this thing, this one, this is an inductor. Inductor, okay. And this was also an inductor. Okay. Sometimes we use transformer also in some solution. Right. So you see, when we develop something in lab, okay, they are quite relaxed and arranged in a much flexible manner, so that we can, if something goes wrong, we can take out it easily and replace. And then if I want to see some voltage, I can easily put my voltage probe or oscilloscope probes here, and you can see it. But when you develop thing for real life application, for a product, okay, how they look like? They should be much compact, fit in a required space. So let me show you this difference between prototype and product. What we develop in lab in 1 or 2 quantities, these are prototype, okay? But product is what? Which goes actually into the application, okay? So this is how a product looks like. So this one is an example of a DC to AC converter, which is used in as a motor controller for electric three-wheeler. Okay, you see those three-wheeler, Toto, TomTom, or e-rickshaw, whatever you call it, right? So that motor controller, and these are the inside view of that controller. Okay, so you can see this capacitor. You see those switching devices here. This one is the heat sink. So you can analyze which part is what, capacitor, etc. Okay, and this one, this is a motor controller for an electric vehicle, four-wheeler. It is a famous company. Due to some legal issues, I cannot disclose it. But you can see this picture taken by me only. You can see this is my hand, and so I'm not allowed to disclose it. You can see this is how it looks like. Okay, these are the capacitor. Here is a quite powerful semiconductor switch. Okay, 2 switches are there in the one leg. So what are the how this motor controller for electric vehicle works? All those things we'll see slowly. Okay, and these are some of the important switching devices that we are going to study in this course, in starting from tomorrow, not today. Okay, slowly, and otherwise you won't be understand power electronics much. So this is an example of MOSFET. Thyristor I was referring to how it looks like. So this diode, how it looks like and all. Okay. Just I would like to highlight here one point to be very clear. You have learned diode in your signal level circuit, right? Maybe in first and second year. So what was the main part of a diode? If I want to see the construction, it has 2 parts, right? What are they? Do you remember a diode? What is consisting of? What is the main material? Diode. Quickly.
Yeah, P part and an N part.
Exactly. PN diode, right? But the diode that we are going to discuss in power electronics, it actually has 3 parts. So how do we define? We define it P plus, N plus, and N minus. Okay. So N plus and P plus indicates high density of impurity, right? You know, we have to add impurity and all. Let me not get into that. And N minus indicates lighter concentration, lighter doping. Okay. So please remember the diode you have studied in first or second year is not exactly the same diode that we are going to study in power electronics. There is one extra layer. Okay. That is why this diode, we'll call it a power diode. Why? By adding that extra layer, it can withstand higher voltage, and these are constructed so that most of them can carry quite high current also. Okay, so that is why it is a power electronics. So a lot of people define it like that. It handles higher power, higher voltage, higher current. That's why it is more powerful than your regular electronics. Okay. Same thing goes with MOSFET also. The MOSFET you have studied in your first or second year. Construction wise, the MOSFET we are going to study in power electronics is slightly different, but basic philosophy is same. Okay. So ideally, you should call them power MOSFET, power diode, like that. Okay. Power BJT. But as we go along the course, I'll be using just diode, BJT, MOSFET. But at the back of your mind, you should always remember it is not exactly same as the power MOSFET, BJT diode you have studied in your first year or second year course. Okay. Of course, how these are constructed, we'll discuss slowly. This I'll come back and we'll discuss that. Now you can see there are so many switches, right? We have different kind of switches. So in what application you use which switch? How do you decide? What are the present emerging switches? So you can see this gallium nitride and silicon carbide. Okay, gallium nitride, silicon carbide. These are the two upcoming devices. Already they are being used, but these are mostly going to be the future. Okay, and present day we are mostly based on silicon. So semiconductor device, you already know silicon and germanium was very popular, right? In your diode you have studied. But in power electronic system, we mostly use silicon device, not germanium. Okay, silicon device is presently the main constituting material for the switches. But next coming up thing, already it has came up and still improving, it is not matured yet, is this gallium nitride and silicon carbide. We call them wide bandgap device. Okay. So these are the emerging switching devices. But germanium we don't use much. Maybe you can take it as a homework, why not? Right, and this I'll discuss later, and for which application you use which devices. Fine. I think I'll just take 2-3 minutes more, and then we'll have a short quiz, and then we'll take break for 5 minutes, and we'll come back. Okay. So bear with me for next 4-5 minutes. We will take up some example of this different power electronic converter, and maybe we'll take a short break after that. Okay. So hold your patience. Right. So we studied 4 power electronic converter types. One is DC to AC, another is AC to DC. Basically, this already you answered this. So let us take an example now. AC to DC converter, we call it rectifier. You have already studied it. More advanced thing we'll study in this course. So in input is this kind of AC, output I want flat DC. What do you think? What could be the examples? Some of you please let me know. What do you think? What will be the example?
Like in adapter of mobile chargers.
Yeah, mobile charger. Extended. Very good. Anything else? So mobile laptop also, right? Same thing. Okay. Anything else?
Electric vehicles, sir.
Electric vehicle, which part? Where?
I don't think so.
Okay. In electric vehicle, in fact.
In braking, charging the battery when braking, when it is brake is applied on electric vehicles.
Very good. We call it regenerative braking.
Braking is
Very good. It's not regular braking, it is regenerative braking. Very good. Yeah, that's an impressive answer. And some of you said in electric vehicle we use it. One is regenerative braking, and another is basically your battery charger. Electric vehicle use DC battery, right? So how do you charge the battery? From AC supply. So there has to be AC DC converter. Then what about computer power supply? We call it SMPS, or simply think about computer power supply. Any day you open up your computer, you will see that a small power supply is there to give your monitor, to run your processor, etc. So those also, in fact, need DC power supply of different voltages. Okay, and how do you get it? In your home, you have 230 volt supply, right? So that is example of a AC/DC converter. So you just look at it in your home, you'll see so many AC/DC converter, right? In your mobile charger, in your laptop charger, in your computer system, and there might be something else also, right? We'll figure it out. So you see in your home, you'll already you'll see some example. Okay, so maybe if time permits, some of you study this. Maybe this you can take as a homework. What is the inside part of a laptop charger? You break it up, or you see some video where people will break up and will try to show you what are the components. Okay, let's go to next converter type, which is DC to DC. Okay, so in the input is also DC, output is also DC. Okay, can you come up with an example?
Sir, a boost or buck converter kind of setup, like where we have a one DC level and it has to be converted into a smaller DC level, maybe.
So that you are giving an example of the circuit. I'm asking about application.
Sir, in power
Where
bank,
you want this?
sir, in power banks, the like LiPo battery is 3.7 volts and USB voltage level is 5 volts.
Very good. Okay. One. Anything else?
So like some microcontrollers use 3.3 volt power supply, so we have to regulate it if you're using a higher voltage supply.
In fact, in computer also, right? Your monitor may need different supply. In your processor may need different power supply. Some of the fan may need different power supply. So there also you see this requirement. Okay. There will be common AC to DC, and then from several DC, from the DC. Okay. Any other example? One of the emerging recent application, or rather different application. Okay. So
high voltage.
Exactly. We will discuss this. HVDC. Remember that. High voltage DC transmission. You must have studied in first year that we transmit power over AC, right? We generate AC power, then we boost up the voltage, AC voltage, and then transmit the power to longer distance. Okay. But HVDC, high voltage DC transmission, is even better when the distance is more than some break-even point. Will be hundreds of kilometers. Okay, so that is a very good application. A lot of research is still going on in this. One more example, let me give you. Solar. Okay, solar photovoltaic is actually DC, but this DC is not like a battery. Okay, it is kind of a variable DC based on a different time of the day, temperature, output varies. Okay, now if you want to have a battery charger at the output, you want to have a battery at the output, so in between you will be using DC-DC converter, because battery wants a defined type of current, right? You cannot charge battery very high current, or you cannot apply very high voltage to a battery. Voltage is already defined. So if solar voltage varies, power varies, you cannot directly connect it to battery. Okay, we'll see. And that's why I said that if you allow me some extra time, I can tell you more about this application. I can share you some simulation model. You can study how to do these things. Okay, but we'll discuss later on. So solar to battery charging could be an example of DC-DC converter. Okay, let us go to the next type, DC to AC. Okay, simple. At the DC input, AC output. Example,
Like inverters that you use and UPS that you use for desktops.
extremely good. UPS. What is the full form of UPS?
Uninterruptible power supply.
Right. So basically, from AC, you charge the battery, right? When power is there in your grid. And then when a grid is not available during load shedding or something, you convert that back into AC to give your load, right? So that is an example. Extremely good. Anything else? What is the main implication nowadays? Hot topic.
Like motor controllers for BLDC motor.
Motor controller. For electric vehicle is emerging, right? I mean, it's a hot topic now. Okay. Do you know, you have already had a course on electrical machines, right? Do you know which motor is mostly used in electric vehicle? What type of motor?
Induction
PMSM.
Brushless DC motor.
Okay. All of you think, yeah? And then I'll take a vote maybe, because this is what needs clarity. As some of you already said, we want to know about more practical. Let me, these are actually, we need to understand which motor is mostly used or most popular in EV.
Three-phase
Let's take the
induction
four-wheeler.
motor.
Okay, one choice, three-phase induction motor. Okay, then
Permanent magnet synchronous motor.
Yes, sir.
PMSM. Okay, basically a synchronous motor with permanent magnet. Anything else?
BLDC.
BLDC. Okay. Any other option? Okay. Something emerging application is PMASYRM. This permanent magnet assisted synchronous reluctance motor. Okay. Tesla's recent model used this. Okay. Tesla's earlier model, they were using induction motor. Now they are not using induction motor. So let me tell you which one is most popular. Number one is this. Okay, as of now. Number two is this. BLDC is only used when power rating is less than typically 5 kilowatt. Example, two-wheeler.
Sir, your screen is lagging, right.
Sir.
This is a problem with this MS-10. Okay, I'm writing. I mean, slowly we'll get it. Maybe I'll talk slowly. Three-wheeler, rickshaw, etc. Not for four-wheeler. Okay. Can you see those green writings, green text?
So we can only see like UPS, AC battery, motor controller, and those things. Other things that you.
Oh, on the right side, you are not seeing anything?
Yes, now it is visible, sir.
Okay, that's a problem. It is good now. You can see till point number 4.
Yes, sir.
Yes, sir.
Okay. So what I'm telling, first choice is PMSM. Okay, permanent magnet synchronous motor. Second choice is induction motor, but slowly people are going out. I mean, induction motor is not being favored now much. Next part coming up is permanent magnet assisted synchronous reluctance motor. Okay. Now, do you know which permanent magnet they use in motor?
Neodymium.
Example?
Neodymium.
ND FeB. Neodymium ferrite boron. It's an alloy, huh? I mean a mixture. Another is samarium cobalt. I don't know if you can see my writing. Later on, you just try to correlate. Huh? So NdFeB, neodymium ferrite boron, and samarium cobalt. Mostly NdFeB is the main choice. Okay. Do you know what category of magnet these are? I mean, what do you call them?
Rare earth, something like
Yes,
rare earth magnet.
exactly. Rare earth magnet. Any idea where they are found? Can I get them in Kharagpur by doing something? I'm talking about getting them, not buying, manufacturing, or basically these come from mining. You have to dig up some area and then some material you get and then do something. Any idea where do you get this? Yeah, I'm actually
China.
diverting. Huh? I don't know whether you're feeling bored or what. It's slightly diverted. Okay, most probably you don't know. Let me tell you. 95% of world reserve is in China for rare earth magnet. Okay. Out of remaining 5, mostly 3 to 4% is in Brazil. Okay. So you understand how China is.
So it is becoming difficult to relate because, like, whatever you're writing is coming up quite
I'm
little.
not writing. Okay. Yeah, I don't know how to handle this. Maybe.
So you can try and turn off your camera. That might work.
Okay. Okay. Keep it. Can you see the sodium cobalt and NDFeB?
Yes, sir.
Yes, sir.
Yeah. Right. So I'm not writing now. I'm just telling. Maybe you can note down. 95% of this rare earth come from China, and remaining mostly come from Brazil. Okay. So there are a lot of political and economical issues involved in this, as you can easily understand, right? And in fact, China sometimes they already stopped supply of this rare earth magnet to Japan in around I think 2011 or 12. Then they threatened US also that see I'm not going to supply you this kind of rare earth magnet. So now people what they're trying to do is to do a motor design which is based on some other concept. Okay, and that's why this reluctance motor comes into picture. By default, reluctance motor doesn't need any magnet. Most probably this reluctance motor are not covered in your electrical machine course. Example is switched reluctance motor and synchronous reluctance motor. Okay. So, and to make them more powerful, you can add little bit of magnet into them. For example, you can use a ferrite magnet, ferrite, right? Ferrite magnet into a synchronous reluctance motor. So that is called permanent magnet assisted synchronous reluctance motor. Okay. In fact, one of our students has designed this, and maybe in few months we'll be fabricating it as well. And if you remember, a few days back, I had circulated an email that I need some of your help in taking this up next. So fortunately, few of you already responded. And if anyone want to join the team later on, let me know. So this, let me tell you, this motor design is a very specialized knowledge, and very few students or people in India are expert in this. Okay, so we still need more manpower in this area. And with electric vehicle, drone, like that, industrial applications, this motor is becoming very important. Now, people are, you'll see later on the slide, I'll be discussing that people are talking about all electric aircraft. Okay, that is also now is a hot topic of research. Then all electric submarine. Okay, so there you can understand this motor is coming up in even a bigger way. So getting a new motor, new concept design is emerging area of research. Okay, fine. I think I talked too much on this. Let me go to the next. And we also work on this UPS, solar UPS motor controller for electric vehicle. Okay, so if you want to join the team, later on I'll show you some of our work. And if you're interested, you can also contribute. Okay, AC to AC converter, right? An example I already gave. Can you just repeat it? Let me know. AC to SC converter. Am I audible, by the way?
Sir, power stations, like uh, in general in India.
Power station. Can you elaborate slightly what exactly you mean?
Like at the main station, like very high voltages above 44 kilovolts are created. Then at substation, they are stepped down using transformer to 11
So
kilovolts, and then at like
okay, so let me tell you very clearly. See, when you are just boosting up the voltage, step upping the voltage by using a transformer, that is not power electronic system because there is no switching involved in it, right? No semiconductor device involved. It is just a transformer. So that is not an example of power electronic converter. Okay. Power electronic converter AC to AC example is a fan regulator. Okay. And what example you gave, indirectly, that is in power electronic domain, we call it solid state transformer. Basically, what we do, we convert AC to DC, then back to AC. Right? You know, limitation of transformer is that output frequency is going to be same, right? At input frequency. You cannot change it. Similarly, output voltage is defined for a given value. Maybe one kind of step up ratio, one step down ratio, that is defined, right? You cannot control it much. But if you can control it, if you want to control it, for example, a motor drive system, we want the output AC voltage to be varied in a wide voltage range, wide frequency range. Okay, we'll teach you about this later. So if we want something like variable voltage, variable frequency, some of you already told induction motor, right? So induction motor, if you want to do speed control, you need variable voltage, variable frequency power supply. And in our home, we have a fixed frequency, fixed voltage supply. So how do you convert it? First, you convert from AC to DC, then again back to AC. So that effectively it looks like a interesting transformer, right? Solid state transformer using solid state devices, this or electronic devices. So this is an example. Okay. So let us take a 5-minute break, not 5 minutes, maybe 2-3 minutes, and then I'll start again. Yeah. So it is 9:13 in my watch. You take a bio break, maybe. Okay. 9:16 or 17, we'll start. In the meantime, if you have any question till this part, I'll be happy to answer. Okay, let me start again. Actually, there are too many content left, and now I'll be speeding up because most of the important part is few are covered, and remaining I'll quickly try to cover. So till now, what am I audible? Can you please confirm, one of you?
Yes, sir.
Yes, sir.
So
Yes,
till
sir.
now, we understood what are the definition of power electronic converter example, right? Now let us try to understand why we are talking about power electronics. What is the main motivation? Why we should bother about it? Okay. So one of the two main area of power electronics is, you'll see later on, we can tackle the present global challenges. Okay. Now, in global level, the main two challenges as of now, you can see that we need to tackle this global warming, climate change, these issues, right? And to solve this, we have to go more renewable. Okay, and with and we need to use more appliances which are more efficient so that our power consumption can come down, right? So one way is that we put more renewable energy sources into our uh, energy generation business, and when we are consuming them, those power, we should use a more efficient solution so that our energy consumption can be reduced, and by this way we can take a lot of um, global issues also. Okay, so if you want to see that which energy source we are using, because for everyday our life we need energy, right? To turn on a bulb, to turn on a fan, to go from one place to another, we need transportation. Then we need a lot of industrial uh, manufacturing, right, to facilitate you with this mobile phone, whatever you get. Someone has to manufacture it, and in that industrial zone, you need a lot of energy. So what are the main energy source? You'll see that most of this energy is coming from coal, as you can see here, right? This top major source is coal. Then you see oil. By oil, basically we refer here fossil fuels like petrol, diesel. Okay. Then you see little bit on the uranium, then gas, etc. Okay. And if you see right now, we are maybe somewhere here, 2021. I don't know, maybe my writing will come later, but you can visualize it. Near 2000 will be right now. And down the line of 100 or 200 years, majority of these sources, they're going to be depleted. You won't get any oil after that time, the way we are using them right now. Sorry. So definitely we have to go for a different energy sources which will last lifelong, right? Solar photovoltaic, wind energy. And another problem with coal is that coal thermal plant, if you have seen any coal thermal plant, you'll see it actually generates a lot of pollution, right? And that is again contributing to climate changes, global warming. So we should do something so that we generate coal as less as possible. And is going to understand this sort of energy sources like coal, etc. They are contributing to more carbon dioxide in the environment level, right? Which is causing this global pollution, etc. So this slide you refer later on, you will understand that the carbon dioxide in recent time has achieved quite a peak value, and it is still continuing. And you can see the trend, etc. from this, which country does what and what. So let me not go into this detail. But what is more important is that we need to reduce our carbon dioxide emission and other greenhouse gas emission, and we should produce more energy from renewable energy sources. Okay, and when consuming those energy, we should be using an efficient solution so that eventually all this problem can be minimized, right? So let us quickly have a quiz on this, and then I'll go to how power electronic solution is more efficient. I'll explain that. So what are the major component of a power electronic converter? Quickly recap. What are the main components? Can one of you please let me know? Yeah, answer please.
Switch and switch and filter. Sir, semiconductor switches.
and some filtering element, right? Energy storage. Okay. Example, I think, let me not spend time. We already spent too much time. You know, example of all this converter. Okay, let me go quickly. What type of switches we are using? We are using semiconductor switches, right? No relay, circuit breaker, manual switch. These are not main part of power electronic solution. Okay. This also I told you, semiconductor switches are made of, present day it is mainly silicon. Okay. Germanium is not that popular. And this is emerging. Gallium nitride and silicon carbide, these are emerging, right? Upcoming rather. Present and these are okay. And the diode we studied in signal electronics. Regular electronics is not same as power electronics, that you must have understood, that we have an extra layer, right? Okay. And this global warming, etc., we talked about. There are several ways to solve this. You just read through these slides. Nothing much to discuss. Okay. But this is important. I don't know whether you're seeing this slide. Indian power sector scenario. Are you looking at this slide? Is it coming?
It is blank, sir.
No, it is blank. But title you can see, right?
Yes.
Yes, sir.
So here I am trying to show you in Indian context the electrical energy we generate. Okay, how much percentage comes from where? Right. So you can see this is quite recent data. June 30th June 2021, and you see most of our energy is getting generated from thermal power plant, and majority of them is coming from coal. Right. So you know burning coal is again a problem for us. Okay, and you see renewable energy sources is how much? It's much lesser, right? Though it is improving. The Indian government is taking a lot of steps, and it is, especially solar is quite increasing. Okay, so you refer to this data and you'll understand. Fine. The next slide it is going to be even more informative. So here, what I try to show you is that, let's say we talk about a thermal power plant. Okay, so finally, sorry, at the initial level, you will be burning coal. And by burning the coal, you'll be generating steam maybe. Using that, you'll be rotating a generator that will produce electricity. Then that will be step up, right? And then after the transmission network, it will be step down again. And finally, you will get in your home maybe 230 volt for different uses. 230 volt single phase or 3-phase 414 or 400. Right. So in this entire journey, from starting from burning the coal to finally when you are using your light or fan in your home, in these different stages, you see the efficiency figures. Okay. So if you assume that you started with 100% as energy, okay, maybe energy stored in coal, that is an 100%. That 100% translate into 16.7% finally when you are using. Okay. That is the loss. You can see roughly 1/5 maybe is just went into loss at different stages of this journey. Thermal power plant is not very efficient, hardly maybe 40% or 35%, right? So a lot of power is already lost there. Then in transmission line, power is lost. In distribution, power is lost. Whatever equipment you are using to generate use electricity, light, fan, etc., they also have efficiency issues, right? So crux is that, always remember, if you are using a 1 watt of electricity in your home, just 1 watt, at the back of mind, maybe 6 watt is actually being utilized to generate, to finally give you 1 watt. And that is the important. I request each and every student, in fact, my family member, everywhere, that even if you can turn off the light when it is not required, you're saving. Don't think about saving 1 watt, right? It actually you're saving 6 to 7 times in reality. Okay, because to generate this 1 watt, you need more than 6-7 watt finally. Okay, so be very careful on this point. Whenever you don't need any electrical appliances, you don't need them in use, turn them off. Okay, as much as possible, because you should be very clear about it. It's not that I'm saving 1 watt. I'm actually saving much more than that. Okay. And that is the reason this power electronic system is so important. If I can improve the system efficiency by even 0.5%, that is a big achievement. Okay. Because let's say a mobile charger efficiency, if you can improve by 0.1%, right? Think about it. How many people are using mobile charger? And this 0.1% is multiplied by what number? And eventually it is leading to what energy saving? It is tremendous, right? You can simply understand it. So I'll tell you an example, another example, why power electronic converter should be used in different application. So we'll take an example of whatever electricity we generate, where do we consume it? Majority of the power consumption from electrical zone actually goes into motor drive, right? Every home you have so many fans. Then in industry, a lot of motors are there. In elevator, motor is there. In your electric vehicle, motors are there. So different area, motor is the main power consuming source for electricity. Okay, and majority of them are actually fan or pump type load. And their characteristics is something like that. The torque is proportional to speed square. Okay, so there is a course on electric drives. You will be getting it in final year. There, these things will be discussed in much detail. But just assume that this data are correct as of now. The torque is proportional to speed square. So you know mechanical power output is torque into speed. So that is proportional to speed cube. Okay, speed I am denoting by omega. And from that, you have a pump, water pump. And you want to deliver water to your agricultural field. Okay, so you have a motor which is giving AC power supply, and you're running the motor. Then it is a pump is there which is giving water to your agricultural field. Now let's say after some time you started with 100% flow, but after some time you wanted to reduce the flow to 60% because you don't need that much water anymore. So what you will do, one option is that at the output of the water flow arrangement, you use some sort of bulb so that you compress it, right? Like we do with the tap, okay? That we tighten it up so that water flow reduces. Another option, maybe you keep on taking out 100%, but 40% you divert to some other area, and 60% you keep on using for your agricultural field. If you do this kind of solution, which is a traditional solution, you see that your input power reduces by a small margin. Still, you need much of the input power, okay, to deliver that 60%. Even though your requirement has come down, you still need at the input power quite closer to the 100% availability. But if you think about a solution where instead of playing with the very pump output, you play with the motor speed. Difference between these two solutions is one is fixed speed and one is variable speed. So this should be obvious to you that if you want to control the output of water output, you can also control electrical motor speed, right? So if you apply this kind of solution, you will see that to reduce output from 100% to 60%, your electric input power requirement goes to just only 22%. So in one case, you need 86%, another case, you need only 22%, right? If you apply a variable speed drive solution using power electronic converter. So you can see there is a drastic improvement in the efficiency. And this will show you, I'm not going to discuss some number. If we can replace all the motor by this kind of variable drive solution, you see there is a huge change that will reflect. Okay. So again, it's just a data you just look on in your free time. Okay. So now I'm telling you about case 2, where I'll tell you very interesting point regarding those conditioning, control, etc. a little bit. Okay, so please pay attention, and maybe just after this we'll have some application and then we'll wind up. Okay, so if I tell you that you design a DC-DC converter for me, so let's say I have 100-volt input, and at the output I want 30-volt. So can you suggest a solution for this? It's a DC-DC converter. What kind of solution do you think it is good? Simple solution, right? Whatever you've studied. Any solution? Is the problem clear statement? I'm not audible.
Yes, sir. Yes, sir. You're audible. So we can use a resistive divider, but that will be lossy.
Exactly. That's the point. So let me tell you. I mean, but let's go to the journey quickly. What are the drawbacks and advantages? So simple solution, use a voltage divider, right? So you want 100 volt here, you want 30 volt here. So 70 volt has to be dropped here, right? As simple as that. Okay. So, you know, this power is V square by R, right? So 70 square by whatever is this R value. That is simply will be the power lost in the resistance. Okay. And of course, by using a fixed resistor, you won't be able to control this voltage. To control this voltage, you have to vary this resistance value. It has to be a variable resistance. Okay. Another solution could be, so how all this formula is very easy. You will spend some time. Another solution is using a BJT, okay, or transistor. But here also you will figure out, so we call it linear regulator. Why? Because we are not turning off and on this particular switch. Okay. It is worked in the linear zone. You must have studied I versus V characteristics of a transistor. Fine. So that is linear device working in the linear zone. So here also same problem. If you want to have 100 volt here, 30 volt here, 70 volt has to be dropped here. Okay. By controlling the base current of the transistor, you can actually control how much current you want to, what should be your collector current, and by that you can control this voltage. But here also you see there is a huge loss. Okay. So let's try to understand quickly, and this forms the basis of power electronics. Okay. So all of you, I need your full attention here. Okay. Please understand this point, and then you can go a bit faster. So here problem was that we wanted to use an intermediate element, right? But we found out it is quite lossy, right? So if you want to use 100% efficient solution, this element should have been lossless, right? We want it to be lossless. So we know the power in a resistance is V into I, right? So if I want it to be lossless, power has to go to 0. That means either voltage or current has to go to 0. Okay. When voltage will go to 0? If the resistance value is 0, right? If resistance is 0, it is as good as a short wire. Okay. So then there is no voltage drop across that short wire, right? Because there is 0 resistance. Something short circuited, that means in that path there is 0 resistance. So that is one possibility. Another possibility is make I 0. So how can you make I 0? Make resistance infinite. Okay. If resistance is infinite, current has to go to 0. So these are the two ways, two values of resistance RC by which I can achieve 100% efficiency. Okay. So let us see, can we get such element in reality? Okay. So example is this switch. A ideal switch, when it is on, right? This switch, when it is on, the circuit will be something like this. There is no resistance, right? The switch is on, it is shorted this branch. So this emulates this circuit. And when switch is off, right, then you can see there is no current. So that means RC as if it is infinite. So this is that case. So by using this particular switching arrangement, we can achieve 100% efficient system, right? So how can we do that? But so this is the concept of switched mode power. The difference between linear it is a linear solution. You see, I don't know. Right now I'm in slide 30. Are you on slide 30? Just check.
Yes, sir.
Yes, sir.
So
Yes, sir.
this is, yeah, good. Thank you. This is the difference between a linear solution and switched mode solution. So here in linear solution, our switch is always on. Okay, I just control its operating area, right? Operating zone, but it is always in linear zone. It is not on off on off. In power electronic solution, it is actually on off solution. It is switched mode, switch on, switch off, not linear mode. So these are the main difference. So now let's try to understand if I use this kind of solution, okay, finally how we can control the output voltage. Remember, our expectation was input voltage was 100, output voltage was 30 volt. Okay, so let's try to see how we can get it. We are going to do, we'll assume a time period, okay, T. Please pay attention, this is very important. And so we'll follow the same thing repeatedly. Okay, that's why this is the time period. T is time period. So in this time period, there is some time when I'm turning on the switch S and some time when switch is off. So simply you can understand when switch is on, the output voltage will be same as input voltage because these are just parallel connection. And in between there is no voltage drop. Okay. And when switch is off, current has to be 0 in the circuit. So output voltage has to be 0. As simple as that. Switch on, output voltage same as input voltage. Switch off, output voltage is also 0. Okay. So what is the average output voltage? How do I calculate? We'll apply simple formula that we learned in first year. So output voltage will be D time input voltage. Output voltage is V0 average is D time input voltage. What is D? D is duty ratio, which is a ratio between the on time by total time period. Okay, this you can simply spend 2-3 minutes, you'll get all this derivation. Okay, so here crux is that if I fix my T, the time period, by varying the on time, okay, I can vary this ratio D, small d, and that's how I can control my output voltage. Okay, so maybe I can write a program in my microcontroller which will generate suitable duty ratio. Okay.
But sir, does this setup not give us an alternating waveform?
Yeah, very good. I was going to ask you what is the drawback of this approach. But see, it is always DC. I mean, it is always unidirectional at least, right? It's always greater than 0, correct? It is not negative. But what we wanted was something like this, 30 volt. What we are getting is something like this, is 100 volt.
So you can use an inductor to smooth out the output.
Exactly. Right? So that is what I'm going to take you. That is the meaning of conditioning. Okay, so let's go step by step. So here you understand problem is that range of D can be 0 to 1, right? Because on time cannot be more than T. It is hardly it can become T. Okay. So this range of D is 0 to 1. So one limitation is that your output voltage will be always lesser than input voltage. So if I want say input voltage 100, output voltage 120, this solution cannot give me, right? Not possible. Okay, but problem is output voltage is not flat DC. It is having pulses. Okay, so how do I solve it? So we'll apply Fourier series simply. Okay, to understand what are the component of that output voltage. You have already gone through Fourier series, so I'm not going to discuss that much. Just solve this circuit waveform. What you'll see, there is an average value which we want, right? That 30 volt. And there is some AC component, as some of you already suggested. These are the AC component, which we don't want. AC component we don't want. Okay. So those who have studied Fourier series, if you remember, if this signal has 1 kilohertz frequency, 1 kilohertz, okay, just an example, huh? This T, 1 by T is F, F is frequency, is 1 kilohertz. Let us assume, okay. So this, due to symmetry, we'll figure out that one of sine or cosine will be eliminated entirely, okay. Do this exercise. So basically, we'll left up with either cos or sine, right? This, due to this symmetry from Fourier series. Then you will figure out the frequency component, this sine or cosine, whatever, you figure it out. What will be that component of the frequency? Any idea? Of that AC part, what will be the frequency component of the AC part?
The odd harmonics.
Exactly. So it is 1 kilohertz will be the fundamental, right? Then 3 kilohertz, then 5 kilohertz, so on, right? Only odd harmonics. So what we want, this plus a 0 hertz signal, which is that average value. Finally, we are getting at the output. So I want to retain 0 hertz, but I want to eliminate all those more than 1 kilohertz frequency component from my output. So what do I use? Most of you will agree that we should use what? To eliminate high frequency component, but to retain low frequency component. What type of solution I should use?
Low pass filter.
Low pass filter.
Low pass filter, right? And how do I construct a low pass filter?
RC circuit.
But in power electronic solution, I don't want R. I told you. Then, so let me tell you this journey. It is actually interesting. I mean, at least interesting to me. Let's see whether you are interested or not. So everything I told you is written over in this slide. Basically, that you first analyze what is the frequency component. Then you understand there is a DC component, there is a AC component. We want to eliminate the AC component. So I have to select a filter, as most of you already said, but I don't want to use a resistance, right? So what simply I'm going to do, I'm using a filter which should be either L or C or a combination, right? Higher order. I should use only L, only C, or a combination of LC, right? Remember, I told you main component of power electronic converter is semiconductor switches and this filtering element. Okay, so no resistance, please. Okay, so this is very, you should note down. As much as possible, we should avoid it. Again, reason is high efficiency. That is what we want. So now, let me quickly tell you about this step. How can you think and how can you actually solve these problems? So most of you will agree that in rectifier, you must have studied, right? We use a capacitor filter parallel to the load. Do you agree? Remember, half bridge rectifier, full bridge rectifier, you used to add a capacitor, right? So that you can make the output voltage flat. Otherwise, output of full bridge rectifier used to look something like this. But then you used to take capacitor. I'm trying to select a different color. Maybe it will come slightly late to you. So then output would look something like this. Okay. By adding a capacitor. So let us try to understand if I, Acha, do you remember, can you, one of you please confirm, do you remember adding capacity filter to the rectifier output?
Yes.
Yes, sir.
Yeah, exactly the same reason, right? There also you had this AC component and you wanted to have only a DC component. So there you used to use a capacitor in parallel to the load. So let us put a capacitor. Right? You can see this capacitor parallel to load. Is that okay? So if you're seeing the capacitor, I want you to think whether this solution is a good solution for this particular circuit. Forget about rectifier. Think about this circuit, whether it is a good solution. Whether I can use this. Is it a feasible solution? What do you think? Whatever is coming to your mind, you can tell, right? We can discuss. This is that ideal switch, huh? Forget about other thing. Assume that this is just a switch. Forget about the symbol now. It's an ideal switch. Do you think this is a good solution?
So even after this, we will get a bit of, I mean, the green type waveform that you have shown. So we might need to use a regulator as well. But otherwise, I feel this is, I mean, this will filter out the major pulsating DC component.
Okay. So you mean to say instead of getting this kind of flat DC, I may be getting something like this, is it?
Yes. Yes.
This is the only problem that you're thinking, right?
Sir, when we are drawing current, the waveform might collapse again to like square wave if we are drawing more current through the load.
Sir, actually it depends on the capacitor size. For example, I don't know what was her name. The suggestion she said this ripple is inversely proportional to the capacitor size. If you put on high capacitor, this actually goes out. Okay. Okay. Well, I'll come back to a more serious problem. It's remaining. Yeah. Go ahead. You want to suggest anything else?
So like there is no resistance in the charging path. Like you said, it's an ideal switch.
This is the biggest problem, right? Electrical engineering, there are two main constants. Two voltage sources of different values should not come into parallel, right? And an inductive circuit should not be broken. Inductor current should not be discontinuous. These two golden rule, every point of time you should remember. Okay, so think about initially, this is 100 volt, input is 100 volt. What was the capacitor voltage at the 0 instant? It was 0 volt, right? Let's say I just starting to give turn on and turn off the switch. Initially, capacitor will be 0 volt, right? For the very beginning, I'm talking about. I have not started turning on the switch yet. I'll turn on at t equal to 0. Okay. Maybe last night I had a good sleep. Then in the morning 10 a.m. I'm going to start working this solution. So by that time, my capacitor is fully discharged. It is 0 volt. It is 100 volt. As soon as you turn the switch, two voltage sources are coming in parallel. And what will be the problem? Anyone?
There will be heavy amount, I mean, a very sudden change in the voltages because we are connecting two non-equal voltage sources in parallel.
Only voltage is problem or current is also a problem?
Yes, current as well.
Current will be discontinuous, right?
Current will be a kind of impulse current, right? It will be suddenly very high. Ideally, it should be infinite, isn't it? This current, I'm talking about this current, switch current.
Yes.
It will be very high, right? Impulse kind of behavior. So your switch may burn actually. Do you understand this? Or you have any confusion? You are connecting a uncharged capacitor to a battery, maybe 100 volts. So capacitor has to quickly get that 100 volt. How can you get it? It has to do infinite current, right? Because VC will be what? Capacitor voltage equation.
So it will be 100 UT.
I equal to C dV by dt.
I equal to C dV by dt. Okay. Right. So you can understand that in almost 0 second, this dV has to be 100.
Yeah.
Okay. So this dt will be very, very small, maybe nanosecond, right? So this current is going to be very, very high. So this may burn your switch. So in between, you must provide something to limit the current, isn't it? And this is not only problem at the beginning. Let's say I turn on the switch and I was happy. Then this capacitor voltage suddenly went to 100 volt. But then after some time, I'm going to turn off the switch, right? Because I have to control the output voltage. If I keep switch always on, the output voltage is also going to be 100 volt, isn't it? So if I want to reduce the output voltage, I will be turning on and off the switch. And when I turn off the switch, then this capacitor has to supply to the load. Capacitor voltage will be less than 100 volt. So again, next time when you're turning on the switch, same problem will come. Okay. So this is not a feasible solution in our engineering approach. So I have to, for limiting the current, I have to do something in between. So what you can do? That is the question. Can I add resistance? No. What can I do?
So inductor.
Exactly. Because inductor is lossless. So let me put an inductor. Is that okay? So it looks like a low pass LC filter basically. You see this LC is a second order LC filter, low pass filter. So are you happy with the solution now? Does it solve? Remember, I told you there are golden 2 rules of electrical engineering, right? Which we should follow each and every point of time. It will solve a lot of your doubts and problems. What are those 2 rules? Capacitor voltage, 2 voltages should not come in parallel. Inductor current should not be discontinuous, right? Should not be suddenly disrupted. Okay, so capacitor voltage problem we have solved out. What about inductor current?
Like when the voltage is 0, at that time inductor current has to suddenly fall to 0.
Which voltage is 0 you're talking about?
So if the switch is suddenly disconnected, then the current would be suddenly 0.
Inductor current has to go to 0, right?
Yes, sir.
When switch is on, inductor current was having some value. As soon as you have a you turn off the switch, inductor current is going to be 0. So what is the problem with this technically? Let it go to 0. Why should I bother?
There'll be a very high voltage across the inductor.
Yeah, exactly. Because VL is voltage across inductor is L di dt, right? So again, same problem here. You see, in very short amount of time, when switch is turning off, inductor current has to go to 0. So I2 minus I1 you understand, and T2 minus T1 you try to realize. This is roughly you can visualize dt di by dt. So I2 has to go to 0. I1 must be some value, right? Maybe say 10 ampere. So this value is minus 10. This value could be nanosecond, right? Maybe let's say 1 nanosecond, 10 to the power minus 9. So you can understand what will be this value, right? It's very large and it is negative. So simply this large voltage will come appear across this inductor, and due to KVL, this switch will simply get damaged, right? Because this is a voltage source, this is a voltage source. So that additional voltage has to appear across the switch, right? If you want to satisfy KVL, then the switch will burn. Okay. So I should provide a path for the inductor current to flow when switch is turned off. So before switch was turned on, current in the inductor was flowing from left to right. Okay. So when switch is off, I should provide a path for the inductor current to flow on the same direction. That is important. Okay. So how do I do it? We put a diode like this. Are you getting this point? So when switch is off, the current will be like this. And when switch is on, diode has to be turned off, because you can see it is reverse bias when switch is on. Okay. Is that clear to you? Anyone having any doubt in this? I think we should stop here. There is some other part also to it that I'll talk about tomorrow. So I'll stop here. It is 9:58. Let me know if you have any doubt, or you can now leave and you can maybe join next class. If you have any doubt, let me know. Else you type it in the chat box. Maybe in my free time, I'll get back to you. Okay. So this, and there is one more capacitor sometime we put in the input side that I'll discuss next class. Okay, then let me stop over here. I'm stopping the recording now.